Okay, so you just told me that the earth is pulling you down, right? Why? Ben's in the middle of eating and he's going, because the earth is big?
Yeah.
Okay, the earth is big. What is it only is it only because the earth is big that it's pulling us?
No.
Do little things pull you as well?
Yeah. Yes. Much.
Nick is saying like this. So is this monkey pulling on me
Yeah. Yeah.
right now?
Yeah.
Yeah?
Yeah.
Why?
It's
Because it can. Yeah, you're right, Dario. This is made of matter. Does any matter pull on any other matter?
Yeah.
And does that matter?
Yeah.
Can't resist, I'm sorry. Yes, it does. If that's true, why does this monkey not come near me and go,
Because
Ben?
the mass of the monkey is really small, so its gravity is really weak.
Go ahead. Okay, so the first part was the mass of the monkey is really small. So it's less pull. But it is pulling me, right?
Yeah.
I just can't feel it.
Yeah.
But there is a pull.
Yeah.
Nick, what were you going to say?
I just have a question.
Go ahead.
If you were on a frictionless plane, would you and the monkey eventually slide together?
Yes. So if the monkey and I were out in space, actually, can I use two of similar mass objects, like these two things? Yes.
But what if you were on Earth and it's just no friction?
Same thing. If we're out in space, nothing slowing us down, no friction, whatever, I hesitate to admit to you that I have done this, but I have worked out the math between this object and this object. And if you let them go in space 1 meter apart, this is what it will do. Yeah, have I told you this already?
Yeah.
Oh, I'm repeating myself. Okay, I'll speed it up. 3 days later, it goes bump, 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 like that, right? And so you will end up stuck together. But it takes a long time because it's such a small force. Okay, why do I drop this and it goes to the earth?
Because there is a bigger mass, like gravity on the object.
Here's a question. What parts of the earth pull on you?
Everything of the earth.
Every single little atom of the earth is pulling on you. So why do we only get pulled down? Or do we?
Kinda, yeah, it's only
Relatively
to
to
the
where
core
we
of the
are.
earth.
Relatively to where we are, it's down?
Because someone is
Montreal is that way. Is Montreal pulling on me?
Yeah.
Yes.
Yeah, it's much further.
It's weird, but is the Pacific Ocean pulling on me?
Yeah.
Is the center of the earth pulling on me?
Yeah.
If you go, do you know what's all the way through the earth on the other side?
Core. No.
Yeah, but if you went through the core all the way to the other side, it's actually the Indian Ocean. I used to think it was China, but it's the Indian Ocean. Did you know that? Why is he freaking out? Huh? He said, did you say Indian Ocean? Oh. Okay. Well, I think it's the Indian Ocean. But anyway, it doesn't matter. So you are being pulled in multi-directions. You're being pulled that way, and that way, and that way, and that way, and this way, and this way, this way. But most of all, you're being pulled straight down because most of the earth is right underneath you. There's a formula to find out gravity in any place in the universe. This is called universal gravity. It's up there.
What do you mean by that?
Kurosh points to. Well, right now, you have a way of finding the force of gravity. How do you do it? You take the mass and bend.
Acceleration? No. Acceleration?
Yeah, what you said before. You said times by
What is O?
what number?
9.8.
9.8.
It's like, so
You guys know gravity as you take the mass and you times by 9.8, right?
yeah.
This is Fg equals mg.
It's right there.
Can they see this board on the video? No? Would somebody turn it for me? Actually, alright. Thank you. You guys ready to go? Let's go. Notes.
Is that R?
We're going.
Radius?
Say it again.
Is it radius? AR?
Good question, good question. First of all, what's this big G?
The universal graph.
Good. This we call the universal gravitational constant. And we have a big penguin named Big G. It's not the same as little g. Little g is 9.8. Excuse me, but where is little g 9.8? Right here on Earth. That's it. So, because we're always on Earth, it makes sense for us to just times things by 9.8 because it's always 9.8 here. But if you were out farther from the Earth, or you want to find gravity between a satellite and the Earth, or two planets, or stars, or galaxies out in the universe, we need a different formula. It's not 9.8 anywhere but here. So we use this. The universal gravitational constant is a number. It's the same, as far as we know, everywhere in the universe. Isaac Newton worked this out. It is 6.67 times 10 to the negative 11. That is big G. Max.
How did he figure that out?
Well, by looking at the planets, and you can work out the proportion of mass versus other things. We'll kind of get there when we do circular motion in grade 12. I'll show you how we did it. Yeah, Ben.
If there was another planet like the exact same size and like mass of Earth, would it have 9.8?
Yes. Ben says if you had a different planet, but same mass, same size of Earth, would it also be 9.8? The answer is yes. What if it was the same mass but smaller?
Same thing. What? Oh, we're stronger.
Way stronger.
Because everything's like much.
Because you're closer to the center, right?
It's like black hole.
So a planet that's more dense has a way higher G, little g. What about something like Jupiter that's more massive and bigger? It is stronger, but not as much stronger as you might think. I think it's like 2.5 times us. Even though the mass is many, many times us, it's bigger, so you're farther from the center. So the distance makes a big difference. Okay, what are these M's?
Mass of big mass. Big mass.
Big M is, yeah, you could call it big mass or mass 1, and little m is mass 2. It doesn't really matter which one is which. Oftentimes we deal with a planet and the planet pulling on something, but they're the same. So they're interchangeable. If you have a satellite that's orbiting the Earth, is the Earth pulling on it?
Yeah.
Yes.
Yeah.
Is the satellite also pulling on the Earth?
Yeah.
Yes. So you're really finding the force between them, right? The force is the same. Okay, and the last one is the R. R stands for radius because Newton, you guys are in school, right?
Yeah.
You're gonna have to learn a long time to get to the edge of human knowledge, where you're learning stuff that nobody else knows. I'll bring you to the frayed edges this year and next year. But you gotta learn a lot of stuff. In Newton's day, you just walked outside at night and you were at the edge of human knowledge. When you look up, what do you see? Stars and planets. We could see, we knew there were bright lights up there, but we didn't know what they were. We knew they spun around if you watch all night. And we knew you could go to one star and that would take you north. But that was kind of it. We didn't really know what they were. And so Newton's big deal was about the planets. That was the mystery of the day. And so this R really means distance between the centers of the objects. So it's really a distance. And it has to be between the centers. And I'll say between the two masses. So if it's the Earth and the Moon, you go from the center to center. If it's a monkey and a toy rocket ship, you go the distance between them, center to center. Sometimes that matters and sometimes it doesn't. I'll show you. It's R because if you have the sun, hold up your fist. Imagine this is the sun and this is a planet. Which planet do you want it to be? Jupiter. So Jupiter goes around the sun in a circle, right?
Yeah.
And Newton knew that. What is the distance between the two?
I don't know, but it's fixed.
Yeah, but what could we call it if it's moving in a circle? It's the radius, right? So the distance between the planet and its satellite, or the star and the planet, that's the radius of the orbit. But it's really just the distance between the two. Okay, so that's how you use this. Take out your calculator. Okay. And put in 6.67. There's going to be a button on your calculator. I've shown you this before. If it's this one, it's second function e's, which is the apostrophe above the 7. And it'll show you capital E. Do not put in times 10. You don't want to do that. Your calculator, if it's not a graphing calculator, it might say EXP. Or it might say capital E, something like that. Then you want to put in negative, not minus, but negative 11. That's big G. Multiply that by the mass of the Earth. The mass of the Earth is 5.97 times 10 to the 24. So you're going to do the e's thing, 24. And then you're going to go, you press equals, and then you're going to divide by the radius of the Earth, which is 6.38 times 10 to the 6. That's in meters. But you have to square that. Before you hit equals, you square the bottom number. And you press equals, and what do you get? Oh, good. Right around 9.8. Yes? Okay, so look closely. If you're looking at this, and you look at this, little g is equal to what part of this equation?
Wait, what?
Little g here is equal to what part or parts of that equation? the FG is the same, and the little mass is the same. So all of this is little g. So if you take big G and you times by the mass of the planet and you divide it by the radius of the planet squared, you can calculate little g for any planet, anywhere, any size. When you do the Earth's mass and the Earth's radius, you should get 9.8. If you're not getting 9.8, then there's something funky with what you're doing with your calculator. Okay. I'm gonna say, let's try to find the force of gravity acting on a 70 kilogram astronaut, and she's at an altitude, which is distance above the Earth, 3.19 times 10 to the 6 meters above the Earth. So here's Earth. And she's out here. Anyone here want to be an astronaut? No? Oh. There's a very, this is a word thing. Altitude is this distance. So how do you find the R in this problem? Is the altitude the R?
No.
No. What do you have to do?
Plus the 6 point. Yeah, the radius of the Earth.
So this part is the radius of the Earth, right? So you need to do the radius plus the altitude, and that'll give you the R. Sorry, that's kind of messy. I'll do that better. In a different color, maybe. So you need the radius of Earth. And you add it to the altitude, and that's going to be your R to put in your formula. Okay, see if you can do that. If you're watching the video, see if you can calculate that, and I'll make a part 2.